Hello, I'm going to talk to you about exchange particles, which is a key part of particle physics. Right, okay, so in physics we say there are four fundamental forces. There are the gravitational force, the electromagnetic force, the weak nuclear force and the strong nuclear force. The weakest of these things being gravitational, because if we want to overcome gravity, we just lift something up. That's me overcoming the gravity of the Earth by using my hand and lifting something up. We can use exchange particles to think about how these forces come about. So if we imagine two people on skateboards, and if I throw a ball from one person to the other person, that person will move that way due to recoil, and that person will move that way. Okay, so a ball has been exchanged and that brings about an effect. Okay, on the other hand, if we've got two people who throw a boomerang from one person to another and that person catches it round that, then that person would move towards. Okay, so we kind of use this idea of exchange particles instead to talk about how forces are brought about. Okay, so what you need to know is for the strong nuclear force, that exchange particle is referred to as a gluon. And if you just think about strong nuclear force as kind of like the glue that keeps the nucleons together in a nucleus, that's why we call the exchange particle a gluon, and pions are an example of gluons. Weak nuclear force, you've got a W plus boson, a W negative boson amongst others. Okay, so these are exchange particles with a non-zero rest mass. They've got a very, very short range. We're looking at 0.001 femtometers, and that's the exchange particle that brings about the weak nuclear force. Okay, the electromagnetic is the virtual photon, which is something that I will discuss later. And there is a school of thought that thinks that there is exchange particle for gravitational, and we refer to that as the graviton. In terms of your A-level studies, you would only need to be aware of these two here, the electromagnetic and the weak nuclear force. However, it is correct to also refer to those two if you want to. Right, now we represent exchange particles in the form of Fineman diagrams, and I will go through the 5 different Fineman diagrams that you need to be aware of. Sorry, I've told a bit of a lie, there are 6. I do also need to talk about the electromagnetic. So, if we have got 2 protons, P and P, they will repel each other when they interact. So, through the space-time continuum, we represent those with arrows. When they interact, that exchange particle is represented by a slightly diagonally upwards squiggly line. And then we have repulsion. Now, something I need to point out to you is this is a representation of the space-time continuum. It's not representing their movement. So if you had a proton and an electron and there was attraction going on, the diagram would still look exactly the same. If we have a look at our table, the exchange particle between these two is the virtual photon. Now, why is it a virtual photon? Okay, if we intercept the virtual photon, the interaction has not happened. Okay, however, the virtual photon is not present until these two interact. So you can't intercept this virtual photon, hence it being virtual. So if you're asked to draw a Fineman diagram, that's what you'd be drawing for electrostatic. 4 marks for referring to these, for the arrows, for the slightly upwards line, and then for labelling your exchange particle. Right, okay. So what happens if we have a neutron and neutrino interaction? Well, for a neutron and neutrino interaction, we know that the other side would be without charge overall, and that's because the charge on this is 0 and the charge on this neutrino is 0. We also know that we've got a baryon and we have got a lepton. So on the other side, we would have a proton, because that is +1, and we would have an electron. Okay, now the reason why this must be the case is because proton is +1, electron is -1, that's a baryon, that's a lepton, that's a baryon, that's a lepton. Therefore, the whole thing is satisfied. And for drawing this as a Fineman diagram, you have N, you'd have your neutrino, they'd move towards each other in the space-time continuum. You'd have your upwards squiggly line, you'd have your proton, and you'd have your electron, and then you'd have to label your exchange particle. Because this has gone from a neutron to a proton, this is W negative. So it's a W negative boson. If we have got a proton plus an antineutrino, okay, we've got a baryon and we've got an antilepton, which means on the other side we've got to have a charge of +1, and we've got to have a baryon and an antilepton on the other side. So, therefore, that means that we're going to end up with a neutron as our other baryon, and to make sure that we've got another antilepton on the other side, we're going to have a positron. Okay, so that's got +1, that's +1, no charge, no charge. So here, proton and antineutrino, upwards arrow, neutron plus positron, and because it's a proton into a neutron, we have got W+, and therefore it is a weak nuclear interaction. Okay, well, we know with beta decay that a neutron changes into a proton plus an electron plus an antineutrino. So, for beta decay, a neutron changes into a proton plus an electron plus an antineutrino. Now, because we've got 3 on the other side, this looks slightly different. So we've got a neutron, space-time continuum. Here, we've got our exchange particle, and we've got 3 strands that come with that exchange particle. So we've got a proton, we've got an electron, and we've got an antineutrino. Now, the reason why this is the case is because here we have got no leptons and we've got a baryon. Baryon number is 1, baryon number there is 1, so that satisfies. Because the lepton number here is 0, lepton plus antilepton equals 0, so that balances out. Okay, and in this situation, because we have got a neutron going into a proton, we've got a W negative, 4 marks. What about beta positive decay? So what about producing positrons? So this proton goes into a neutron, baryon and baryon, and here we have got an antilepton, so therefore we need a lepton to balance it out. Okay, now I've put an E next to that. Okay, the lepton that's created here is the neutrino. It's actually an electron neutrino, just the same that it would be an electron neutrino up there as well. Okay, so here we've got proton, that goes to a neutron, arrow there, slightly diagonal arrow, that's going to produce a positron, and that is also going to produce a neutrino. And because it's proton to neutron, we're going to have W+, 4 marks if you get asked about that in the exam. Sometimes electrons get captured by proton-rich nuclei, and this is to lower the proton count. So if you've got a proton-rich nucleus, it can capture an electron. So baryon and lepton, so on the other side, that would be a neutron, and that's a lepton, so we need a lepton to balance that out, a neutrino as well. Okay, in this case, we've gone from proton to neutron, so P goes to N, we've got our exchange particle, and the electron has been captured, so the electron capture goes to a neutrino. Proton to neutron, and therefore that is W+. I would thoroughly recommend that you practice doing some questions related to this. Thank you very much.